Swayam Prabha. Digital India. Educated India.
Welcome back to the video course on fluid mechanics. In the last lecture, we were discussing about the pipe systems and losses related to the pipes. So, we have seen that the pipe losses can be classified into major losses, the losses due to the friction and the viscous effects of the fluids. So, we have seen as the major losses, and we have seen the one of the most commonly used equation, Darcy-Weisbach equation and its derivation, and then related so the pipe friction factor, and also we have seen the Moody's diagram and other related equations. And then also we have discussed the minor losses. So, the minor losses are due to the various pipe fittings or say changes in pipe, say like expansion, contraction and other kinds of fittings. So, as we discussed, the losses can be major losses and minor losses. So, we have seen that this minor losses are concerned, we can put it in terms of V square by 2G, where V is the average velocity of the pipe, and so in terms of we can express the K into V square by 2G, where K is a coefficient or constant with respect to various minor losses like with respect to expansion, contraction, pipe fittings like junction, bends or T junction, then valves, etc. So, this we have seen in the last lecture. So, now further we will discuss more about the various minor losses as far as pipe systems are concerned. So, here, so with respect to the loss due to the gradual expansion, so we have seen earlier a formula with respect to the expansion of pipe. So, when the pipe is expanding from say area of cross section A1 or pipe diameter D1 to pipe diameter D2 and area of cross section A2. So, then we have seen the loss due to the expansion can be written as Ke into V1 minus V2 all square by 2G, where V1 is the velocity at section 1 and V2 is the velocity at section 2, and K is the loss coefficient here with respect to and the various say expansion type. So, with respect to say various experiments were conducted, and then with respect to this transition or with respect to the expansion, say this expansion angle. So, this is the angle theta. So, with respect to this theta, we can find various coefficient, loss coefficients. So, here you can see that it is plotted from say starting from 0 to 180. So, say depending upon how much is the expansion or how much is this angle, then you can see that the loss coefficient is coefficient of say pipe loss is say initially coming less, say starting from about 0.7 it is going down, and then further when the angle increases it is again increasing, and finally again it is becoming constant like this. So, this is obtained through large number of experiments. This gives the loss coefficient K with respect to the angle theta. So, like this, so for contraction also we can just do a number of experiments and see with respect to say how much is the say the contraction, or say like we have seen the expansion like this. So, this is the expansion of the pipe with respect to the diameter change. So, similar way we can have contraction also. So, corresponding to contraction we have also already seen an expression earlier. So with respect to the contraction of the pipeline, we can also, with respect to this angle of contraction, we can find out this loss coefficient Ke, and then we can find out the loss for various angles. So, and then also we have seen this minor losses other than the expansion or contraction. We can have various pipe fittings or pipe junction. So and then also we have seen that when the flow enters from say for example from a reservoir to a pipe, or from a tank to a pipe, or when flow passes from the pipe to a tank or reservoir. So these are there are entrance and exit losses. So here with respect to various parameters in this slide, the type of entrance, and then what kind of entrance is that, and what are the loss coefficients, losses with respect to loss, the loss coefficient, here the losses are tabulated in this table. Type of entrance is square edged like this. So you can see that this is a square edged pipe entrance. So generally the loss will be 0.5 times v square by 2g, where v is the velocity in this pipe flow, the pipe section here. So 0.5 v square by 2g will be the loss with respect to the square edged entrance like this. And then you can see that say if this square edged entrance is say just say it is rounded or made it smooth entrance, so that you can see here the losses will be reduced. So if it is well rounded like this, you can see here instead of this corner edged this thing, it is rounded. So the loss coefficient will be reduced to 0.01 to 0.05 v square by 2g, depending upon how effectively we smoothen it or we round it. So for well rounded entrance, the loss will be varying from 0.01 to 0.05 v square by 2g. And then if the entrance is in such a way that there is a re-entrant, that means the pipe is extending to the other pipe or the tank or the reservoir like this as a re-entrant, then you can see that the loss will be much higher. So it is generally varying from 0.8 v square by 2g to 1 v square by 2g. So this will be much higher than the square edged this thing. And so like this, so depending upon which way we give the entrance or which way the exit takes place, so the loss will be varying, the pipe loss will be varying, and loss coefficient we can say obtained through experiments or the field test. So generally wherever an expansion or wherever an entrance is there, so it is always better to give a smooth transition, smooth entrance or a smooth exit, such a way that the losses will be much less, as shown in this figure for the well rounded case. So this all the exit and entrance losses we can put in terms of this v square by 2g, as we discussed earlier. And then some of the other important say pipe components are like valves, gates. For this also you can see that since these are also either some way controlling the flow, and then there will be definitely the effect of the pipe loss effect will be there. So here in this slide, say depending upon the type of the say the type of the valve or type of the gate, the loss coefficient K will be varying. So and the type of the gate or valve is put here and corresponding K value. So as we discussed, the pipe loss is put in terms of K v square by 2g. So this expressed in v square by 2g, so K v square by 2g. So here when this is say depending upon the valve, gate or valve, say this K value is put here, approximately it is say depending upon the material. So this K value will be varying depending upon the material, what kind of smoothening or what kind of way the way of construction of the valve. So this K will be varying. So some of these standard available values of K are written here. So you can see that if say if the valve is a globe valve, fully open globe valve, then K value will be about 10 as shown here. And then if it is a gate valve, fully open gate valve as shown in this figure, then it is much less, the loss will be much less, it will be 0.15, the K value will be 0.15. And then if it is an angle valve fully open like this, an angle valve, then the K value will be about 2. So this value of K depends upon the material and the type of construction. So generally the manufacturer will be specifying this loss coefficient K with respect to the material and with respect to the type of manufacture and other parameters based upon the test conducted in the laboratory. And then if it is a swing or check valve fully open, then the K value will be about 2. So this is a swing or check valve as shown in this figure. So it will be K value will be about 2, and if it is standard T, a T junction like this, so you can see that for T the flow is going like this and other this way it is diverting. So the K value will be varying from 0.2 to 2, K value will be varying, and then if it is a standard elbow, the K value will be varying from 0.3 to 1.5. So this is a standard elbow which is say for diverting the flow. So it will be 0.3 to 1.5, and if it is medium sweep elbow, same so that the flow will be much smoother and loss will be much lesser, you can see that it will be 0.2 to 0.9. The standard value will be varying from 0.2 to 0.9 depending upon the pipe material and the smoothness given. So medium sweep elbow K value will be 0.2 to 0.9, and then if it is long sweep elbow valve like this, so it is a long sweep elbow, so K value will be about 0.6, and if it is a 90 degree bend like this, you can see that for 90 degree turn of the pipe we will be using 90 degree bend. So here for 90 degree bend the K value will be about 1.2, and then if it is a 180 degree return bend, you can see that it is a return bend like this, so K value will be about 1.5. So like this, say for various valves, various junction T's or various gates, say depending upon the type of material, type of manufacture according to the manufacturing way of manufacturing and how we give the say connection between the main pipe to the valve or with the fittings, this K value will be varying, and most of the manufacturer will be specifying the K value for their products depending upon the material. So we can directly utilize, say with respect to which type of valve we use or which type of gate or which type of bend we use for our same pipeline, we can use the standard value available from the manufacturer. And now say we have already seen, say we are expressing the minor losses in terms of V square by 2G, say the V is the average velocity. So now another important aspect with respect to this loss coefficient which we have discussed earlier, it is equivalent length of pipe. So the loss coefficient can be expressed as a function of equivalent length LE of pipe as. So we have seen this minor losses we are expressing in terms of K into V square by 2G. So for the major loss we are using the Darcy's, generally we are using the Darcy's Weisbach equation, so which is FLV square by 2GD. So we can write this minor losses in terms of an equivalent length, pipe length, so that everything can be put in terms of the say the major friction losses. So that length is called the equivalent length. So to get that equivalent length, we can equate this minor loss K into V square by 2G as F into LE by D into V square by 2G, which is Darcy's Weisbach equation, FLV square by 2GD. So this LE is the equivalent length corresponding to this loss coefficient of minor loss KV square by 2G. So finally, with respect to this equation, we will get the equivalent length as LE is equal to K into D by F, where K is the loss coefficient, D is the diameter of the pipe, and F is the friction factor. So say for the given pipe system or the given system, we can convert, say if there are number of bends, a number of gates, a number of valves, etc. So all these things we can convert in terms of the equivalent length, and then finally we can solve in terms of the major loss, that is with respect to the Darcy's Weisbach equation. So the equivalent length is obtained, LE is equal to K into D by F, where K is the loss coefficient and D is the diameter of the pipe and F is the friction factor. So, now the head loss of the pipe system is same as that produced in a straight pipe whose length is equal to the pipes of original system plus sum of additional equivalent lengths of all components of the system. So, once if we can do this equivalent length calculation for various fittings, pipe fittings, entrance losses and exit losses, then we can write say the total head loss we can write in terms of the existing straight pipe which is already existing, plus we can add the sum of additional equivalent lengths which we got from with respect to the various components of the pipe system as described here. So, now say with respect to various piping components we can also, so as I mentioned this the value of K is given by the manufacturer depending upon the material and depending upon the component, pipe component. So, with respect to this piping components, since it is LE is equal to KD by F, where this say if K is the loss coefficient already known for the given fitting, given component, and F is also known as the friction factor, then this LE by D, that means LE by D will be K by F. So, this for the given pipe fitting K will be it will be constant, it will be known, and the friction factor will be also known, so that we can have this kinds of table, so that directly from the table we can get this. Once the diameter is known, we can get the equivalent length. So, say for example, conventional globe valve LE by D depending upon the material it can be 400, or Y pattern globe valve can be 116, fully open gate valve it can be 10, 50% open gate valve it can be 150, standard T it can be 10, 90 degree standard elbow it can be 30, 45 degree standard elbow 16, return bend 50, like this K by F is given, so that we get in terms of LE by D and the equivalent length by diameter. So, once if you know the diameter with respect to the pipe fitting, we can easily get the equivalent length of the pipe. So, now just with respect to this tabular form, we will just discuss a small example here. Say fully open gate valve is in a pipe with a diameter of 20 centimeter, what equivalent length LE will cause the same head loss as gate valve. So, say now the question here is, say we have got a fully open gate valve in a pipe with a diameter of 20 centimeters. So, we want to find out what will be the equivalent length with respect to this gate valve, so that the same head loss as gate valve. So, from the table you can see that this LE by D, so corresponding to this LE by D here, fully gate valve is 10. So, this 10 LE by D is equal to 10. So, since here the diameter is already given as 20 centimeter. So, the equivalent length will be LE is equal to, say this LE by D is already given as 10 into D. So, 10 into 20 centimeters. So, that will give the equivalent length correspondingly will be 200 centimeters. So, equivalent to this say fully open gate, we will be having an equivalent length of 200 centimeter pipe for the wherever this fitting is done. So, for the pipe system. So, like this we can solve various examples, various problems wherever various fittings are there. We can say find out what kind of fitting, and then LE by D values are known. So, once the diameter is known, we can calculate the equivalent length. Now, another important aspect is, say while we do this kinds of design of pipe design, we can calculate the equivalent pipes. So, you can see that say like shown in this photograph, we will be using different kinds of diameter of pipes, say for example, here one diameter, here another diameter, here another diameter, here another diameter. So, like that we will be having number of types of pipes in a single system. So, it will be easy if we can find out the equivalent pipes correspondingly. So, this we can obtain, say for example, a pipe of length L1, diameter D1 and friction factor F1 will be equivalent to another pipe of length L2, diameter D2 and friction factor F2 if F1 L1 by D1 to the power 5 is equal to F2 L2 by D2 to the power 5. So, this condition is obtained for the same head loss, the two pipes for the same discharge. So, if the discharge is passing is same, then we can obtain, we can use the Darcy's Weisbach equation, and then since the discharge is same, and if we, since with the assumption, say if you say the same head loss is there in two pipes for between with the two pipes, then we can equate the Darcy's Weisbach equation with respect to pipes, and then we can write F1 L1 by D1 to the power 5 is equal to F2 L2 D2 to the power 5. So, from which say we can find out where say the lengths are known and F1 F2 are known, then what will be the D2 in terms of D1, or like that we can calculate the equivalent pipes correspondingly for the given system by using this equation. And then also sometimes say for some kinds of problem we may not be able to use the circular pipes, the diameter say we cannot specifically, depending upon the field condition, we cannot use the circular pipe. So there we can have non-circular ducts. Say for example, this one of the modeling work which we did recently, say from the surge pool here the flow should come through a duct like this, so a tapering duct like this. So you can see that this kinds of problem we have to find out the equivalent diameter for the non-circular ducts. So for non-circular ducts, the hydraulic diameter DH is used as the characteristic length for the calculation of Reynolds number and relative roughness. So for the non-circular ducts which we use for the field problem, we can calculate, we can find out the hydraulic diameter, equivalent hydraulic diameter DH, and then we can solve for the Reynolds number or relative roughness and other parameters. So generally this DH, which is the hydraulic diameter, will be 4 times of the area flow by perimeter of duct in contact with the fluid. So where here this A by P is hydraulic radius, so 4 times of hydraulic radius will be the hydraulic diameter for the given system. So DH is equal to 4 into area flow divided by perimeter of the duct in contact. So we can use this equation to get the equivalent diameter for the non-circular duct. And then for non-circular pipes, the hydraulic radius is say if R is equal to A by P. So for circular pipe flowing full, correspondingly the hydraulic radius we can put as say R is equal to A by P, which will be equal to D by 4, that is equal to R0 by 2. So correspondingly you can see that say R0 is the radius of pipe, so R is equal to R0 by 2, therefore R0 is equal to 2 times the hydraulic radius. So if you want to find out the Reynolds number, so Reynolds number is Vd by nu for the pipe. So where mu is the kinematic viscosity, D is the diameter of the pipe, V is the velocity. So since R0 is the radius is 2r, so diameter is, we can put equivalent diameter as 4r, where capital R is the hydraulic radius of the system, non-circular pipe. So the Reynolds number we can put in terms of 4Vr by nu, and relative roughness will be E by D. So D is now 4r, so E by 4r. So like this, for the given system, for the given non-circular pipe system, we can convert with respect to the hydraulic diameter, the say by using from the hydraulic radius we can get the hydraulic say diameter as described here, and then we can directly use in the calculation of the Reynolds number or the relative roughness for the given system. And then finally, if you want to find out the head loss, we can just substitute to the Darcy-Weisbach equation. We have seen the head loss equal to FL V square by 2GD. So here D is now 4 times R, where R is the hydraulic radius. So HL is equal to head loss will be equal to FL V square by 4R 2G. So it will be 8 FL V square by 8GR. So this instead of D, now it will be 4R, where R is the hydraulic radius for the non-circular system. So like this, for various shapes, various cross section, we can find out the, first we can find out the hydraulic radius, and then we can find out the hydraulic diameter, and then that can be used for the various calculations like Reynolds number or relative roughness or the pipe loss. So finally, as far as this pipe losses are concerned, so as we discussed with respect to the Darcy-Weisbach equation, the pipe flow head loss, you can see that the pipe flow head loss is proportional to the since the equation which we discussed here is FL V square by 2GD. So say HL, the head loss equal to FL V square by 2GD. So this is the Darcy-Weisbach equation. So with respect to this, we can see that the pipe flow head loss is proportional to the length of the pipe. So since HF is equal to FL V square by 2GD, so it is pipe flow head loss is proportional to the length of the pipe then proportional to the square of the velocity, and then we can see that it is proportional inversely with the diameter of the pipe. So, we can see that also this pipe flow head loss is increasing with respect to the surface roughness. So, if we use a more rough pipe, then the head loss will be more. But with respect to this relationship, you can see that this pipe flow head loss is independent of the pressure. So, it is mainly depending upon the velocity, length, then diameter, and also the roughness. It is independent of the pressure. So, total losses in the pipe system is obtained by summing the individual head losses due to the roughness, fittings, valves, etc. So, to find out the total losses, we will sum up the friction losses and then losses due to various fittings, exit loss, entrance loss, or the expansion loss, contraction loss, etc. So, now we have seen the we started with as far as pipe flow system is concerned, we started with the classification of laminar, turbulent, and then we have seen the various relationship for this, and we have now discussed the losses, pipe losses. So, now while going for pipe design or say before pipe construction, when we go for design, we have to see that various kinds of problems, say what kind of problem we are going to solve, whether we have to design the diameter of the pipe, or we have to find out how much is the discharge passing through the pipe, or we have to find out the friction factor or the head loss in the pipe. So, depending upon the the analysis, depending upon the problem which we do, so the approach also changes. So, accordingly we can classify the general pipe flow problem into 3 categories. So, here the categories by what parameters are already given and what to be calculated. So, some of the parameters will be given and we have to find out the remaining parameters. So, we have here generally we can categorize into 3 categories: type 1, type 2 and type 3. So, this category is according to what kind of data are already available and what we have to find out. So, accordingly in the first category, type 1, generally the pipe flow, the fluid parameters like density and dynamic coefficient of viscosity and velocity will be given, discharge will be given, and also the pipe material like the roughness, height and the diameter will be given. We have to find out the head loss. So, this type of problem is the type 1 problem, it is a direct problem, since we have to calculate the head loss. And the type 2 problem, generally the fluid parameters like density, coefficient of viscosity will be given, and the pipe parameters E, the roughness, height and diameter will be given, head loss will be given. We have to find out how much will be the flow takes place or the velocity through the pipe at various sections, we have to find out. And then type 3 problem is, say all the fluid parameters are given like rho, mu, and also the velocity we have to, and also the roughness is given and head loss is given. So, we have to find out, we have to design the pipe so that we have to find out the diameter. So, generally for the general design purpose there will be 3 categories of problem: type 1, type 2 and type 3. So, we will discuss in detail for how to approach these different types of problem. So, for type 1 problems, pipe flow problem for type 1, the question is to solve a type 1 turbulent pipe flow problem, the following procedure we can utilize. So, the given parameters are, as we discussed, the flow properties, fluid properties and pipe geometry. So, the next step is by using these parameters we will compute the Reynolds number, and also we will find out the E by D ratio, roughness, height by diameter of the pipe ratio, and then we can find out the friction factor by using the Moody's chart, or we can use some of the equation like Colebrook equation or the various other equations we discussed earlier, or like a Sami Jain formula. Some of these equations we can utilize, and then we can get the friction factor F, and then once we get the friction factor we can directly use the Darcy-Weisbach equation to compute the head loss HF here for the given system, given problem. So, this is called a type 1 problem. So, this is typically represented in a flow chart here. The flow diagram 1 given rho, mu, V, Q, E and D where rho is the density, mu is the dynamic coefficient of viscosity, V is the velocity, Q is the discharge, and E is the reference height, D is the diameter. So we can calculate the Reynolds number and d by d ratio from the given data, and then either you can use the Moody's chart or the Colebrook equation to get the friction factor, and then we can get the head loss directly from the Darcy-Weisbach equation. So this type of problem is the type 1 problem. So now type 1 problem, as you can see, it is straightforward with respect to the given data. We can use some of the equations like Colebrook equation, and then we can further use the Darcy-Weisbach equation. So next type of problem is pipe flow problem, type 2 problem. So for type 2, the pipe flow problem is, say, it is a little bit more complex. So here, since we do not know the velocity, so we have to find out actually the discharge velocity. So no, we cannot compute the Reynolds number, so we cannot directly get the friction factor F. So the procedure generally for this kinds of problem, the procedure is as follows. The given parameters are fluid properties and pipe geometry, and then we can go for an initial guessing of F from the higher Reynolds number portion of the known E by D curve on the Moody's chart. So we can use the Moody's chart for and we can assume or we can guess the value of F, and then using that value we can compute the V velocity, then we can get the Reynolds number using then say we can use the Darcy-Weisbach equation. So from the new value of F from the Moody's chart, we can using the we can say earlier we assumed the friction factor F. Now using the obtained value of V and Re and E by D, we can get a new value of F from the Moody's chart, and then we can check whether we are converging with respect to the discharge or the velocity which we compute, and then we can iterate. This is so this problem is generally solved as an iterative method. So we will iterate between steps 3 and 4 until convergence. So this is type 2 problem. So it is represented in a flow chart like this. So given rho, mu, E and D, and we will assume F, and knowing E by D, we will calculate get the Reynolds number, and we will compute V, the velocity, and using Re we can go to use the Darcy-Weisbach equation. We will compute the V, and then we will get using these parameters the Reynolds number, and this parameter here we will get the new friction factor from the Moody's chart, and then we will iterate the problem until we get the converged value of the discharge or the velocity which we are looking for in this type 2 problem. So this is the flow chart, flow diagram for the type 2 problem. So now third one is type 3. So here we have to design or we have to find out the diameter of the pipe. So here for the since the diameter is not known, we cannot get the Reynolds number or other parameters. So again here again we have to go for iterative procedure. Since we do not know the diameter D a priori, not only we cannot calculate Reynolds number, but we do not know E by D also. So hence the best approach is we will assume some value of F, say for example 0.0 to 0.02. So depending upon the material we can assume certain values, and then we can proceed. So here the procedure is given fluid properties and flow properties, we assume value of F, then compute D from the Darcy-Weisbach, and then say E by D and Reynolds number, then find a new value of F from the Moody's chart, and then we will iterate between steps 3 and 4 until convergence. So for this type 3 problem, the flow chart is given here. So given rho, mu, V and E, so that we will guess a value of F, the friction factor, and then compute D using Darcy-Weisbach equation, and then Reynolds number is known, E by D. With respect to this, we can use go to Moody's chart and find out the friction factor, and then we can again iterate until convergence. So this is the flow chart for the type 3 type of problem. So like this, say for the given system, when we design a pipe, so we can first classify, we can just check what are the available data, and then what is to be determined. So accordingly we can classify whether the problem is type 1, type 2 or type 3. Then we can see which approach we have to utilize, whether we have to go for iterative procedure or whether the solution is straightforward. And now say generally For pipeline flow analysis, we can use the Bernoulli's equation, and as we discussed earlier, the Bernoulli's equation states that the total energy of the system doesn't change, hence total head is constant. So, based upon say between say when we design a pipe, say for example say here, let us assume a pipe flow system starting from a tank, and then it is going to another tank like this. Say for such a system, if there is a wall or a bench and exit load, entrance loads like this. So, here what generally we can use the Bernoulli's equation to solve this kinds of problem. So, between two sections, say we assume that say when we consider say if this is A, B, C, D, and then say between say reservoir, say the tank 1 or reservoir 1, and this is tank 2. So, we can apply between two sections the Bernoulli's equation, and then the Bernoulli's equation states that the total energy of the system doesn't change. So, hence the total head is constant. So, since we will be considering the pipe losses, the due to friction losses or the minor losses like due to various pipe fittings, all this we will consider, and then we will equate the total energy of the system doesn't change. So, between two sections we can take it, and then we can solve the Bernoulli's equation to find out various parameters. So, this here the Bernoulli's equation is applied by using certain assumptions. The assumptions are used here are flow is steady, fluid is incompressible, friction losses are negligible. That means same with respect to this we consider the friction losses negligible and valid at 2 points along a single streamline. So, with respect to this same here we consider with respect to these assumptions, we solve for the we use the Bernoulli's equation and then solve for the problem. So, now say two other important concept in while doing this pipe flow design and analysis is the hydraulic and energy gradient lines. So, this hydraulic and energy gradient line, so knowledge of hydraulic gradient line and energy gradient line is important in analyzing complex flow problems. So, this energy gradient line means, so we know that say by using the Bernoulli's equation, generally it is P by gamma, the Bernoulli's equation gives P by gamma plus V square by 2G plus Z is constant, where P by gamma is the pressure head, V square by 2G is the velocity head, and Z is the potential head. So, where V is the average velocity, P is the pressure, gamma is the specific weight, so G is the acceleration due to gravity. So, as per Bernoulli's equation, this is constant. So, now the plot of this P by gamma plus Z along the pipeline gives the hydraulic gradient line. So, if we plot for this such a pipeline system, if we plot P by gamma plus Z, so this plot will give, so we can plot for various systems. So, this the V square, so if this is the datum here, and then we can plot P by gamma plus Z. So, that gives the hydraulic gradient line HGL. P by gamma plus Z gives the hydraulic gradient line, and then the plot of P by gamma plus Z plus V square by 2G, this gives the energy gradient line. So, these two lines we can plot with respect to the given pipeline system. One is P by gamma plus Z, which gives the hydraulic gradient line, and we can also plot P by gamma plus Z plus V square by 2G, that gives the energy gradient line. So, since we are using the Bernoulli's equation, it is coming from the Bernoulli's equation, both the HGL hydraulic gradient line and the energy hydraulic gradient line and energy gradient line we obtain from the Bernoulli's equation. So, if you consider this figure here, so here there is a tank or reservoir, and then there is a pipe going like this, and then there is a nozzle here at the end of the pipe. So, say if this is the datum, then you can see that the total head available with respect to datum is H in the at the with respect to this reservoir, and then say we can find out this P by gamma and then P by gamma plus Z. So, this red line here, that will be the hydraulic gradient line, and then if you add the V square by 2g, which is the velocity head, V square by 2g. So, P by gamma plus Z plus P by gamma plus V square by 2g, that will give the energy gradient line with respect to the Bernoulli's equation, which we have discussed here. So, HGL and EGL we can plot along the pipe axis like this, and this shows the, here we can see that the energy gradient line is vertically above hydraulic gradient line by a distance of V square by 2g. So, between the difference between the energy gradient line EGL and hydraulic gradient line is this velocity head V square by 2g. So, for this kinds of problem, say for such a pipeline system like this, we can plot the HGL, the hydraulic gradient line or energy gradient line, and then we can use this also to find out various unknowns, either pressure P, or we can use the either sometimes velocity, or depending upon the case we can solve for various parameters. So, now if the hydraulic gradient line is you can see that here this HGL hydraulic gradient is the slope of HGL if the conduit is horizontal. So, you can see that if pipeline is horizontal, then it will be just the slope of the hydraulic gradient line. Hydraulic gradient is the slope of HGL, but if not, if it is the pipeline, if the conduit is not horizontal, then we can take the derivative. So, d by dl of P by gamma plus Z, that will give the hydraulic gradient if the pipeline is not horizontal. So, if it is horizontal, it is just the slope of the HGL, and similarly the energy gradient is slope of EGL if the conduit is horizontal, as we can see here, it is the slope of the EGL, and if not, that means if pipeline is not horizontal, then we can just take the d by dl of Z plus P by gamma plus B square by 2g as written in this equation. So, depending upon whether the pipeline which we design, the flow system which we design is horizontal or if it is inclined, so we can utilize the corresponding equation, whether it is the directly the slope or the derivative with respect to Z plus P by gamma for hydraulic gradient, or the energy gradient is concerned, we can take d by dl of Z plus P by gamma plus V square by 2g, where Z is the datum head, P by gamma is the pressure head, and V square by 2g is the velocity head. So, now we will just before further discussing various pipe flow systems, we will discuss one simple example here. So, here the problem is, say here we have got a tank here, and it's from the center line of so there is a pipeline located at this here at this 2 meter above the datum center line of the pipe, and then the pipeline length is 50 meter till here, and then there is 10 meter here. So, total 60 meter. There is a nozzle here at this 60 meter. So, now the question is, determine the elevations of the energy gradient line and hydraulic gradient line HGL at the points L, here L, M, N, P and R. So, here the total length is L to R is given as 60 meter. So, we have to find out the elevations of the EGL and HGL at point L, M, N, P and R. So, the data given are the diameter of the pipe, here this diameter is given as 100 mm, and here the total H with respect to the reservoir or the tank here is 2 meter plus 25, so 27 meter, and a nozzle diameter here is given as 50 millimeter, and the friction factor for the pipe is given as, this pipe is given as 0.02, and a nozzle loss here, this with respect to this nozzle, the exit loss. So, here the nozzle loss is given as 0.1 V square by 2g, and the entry loss is here with respect to this entry loss is given as 0.5 V square by 2g. So, for these points L, M, N, P and R, L, M, N and P and R, we have to find out the elevations of EGL and HGL, and also here in the system there is a valve at this location at about 22 meter from the reservoir. We have a valve, a control valve like this, and its corresponding K value is given, the loss coefficient is given as 10. So, for such a system we have to find out the elevations of EGL and SGL. So, as we discussed, so here we will be using the Bernoulli's equation so which including the head loss. First we will consider the Bernoulli's equation from exit point R to the reservoir. So, here this is the exit point R to the reservoir. We will consider the Bernoulli's equation. So, with respect to the reservoir, H is the head, and then if P1 by gamma is the pressure head, and VL square by 2G. So, that is equal to VR square by 2G plus Z plus P2 by gamma plus 0.5 V square by 2G plus FL V square by 2GD plus KV square by 2G plus 0.1 VR square by 2G. So, here with respect to, we are writing the Bernoulli's equation with respect to this location, and then with respect to the outlet of the nozzle here. So, you can see that with respect to this reservoir or tank is concerned, here the total head H plus we will be having the pressure P1 by gamma, actually it is atmospheric. So, it will be 0, and then before this, say here at this just before the entrance of the pipe. So, you can see that here this gives the velocity head, but here the velocity will be, we will be assuming the velocity as 0. So, this location it is VL square by 2G, and then if you take from here the velocity at the nozzle, it is, if it is VR, so VR square by 2G, then we have to consider the various the datum head is Z, here datum head is Z, and then we will be considering the say here this entry loss we have already seen, this is 0.5 V square by 2G, this entry loss. Then we will be considering this for the pipe length, there will be, we can use the Darcy-Weisbach equation to get the head loss. So, FL V square by 2GD, and then we have this valve, so that gives this K V square by 2G, and then what is the loss here, that is the with respect to nozzle loss is 0.1 V square by 2G. So, here in this equation, now the reservoir surface pressure, we will be assuming that the atmospheric pressure, so that this P1 by gamma will be 0, and VL, since it is just before the entrance to the pipe, so VL here will be 0. So, on the left hand side of this equation, it will be only H, that is equal to 27 meter, and on the right hand side you can see that here the pipe diameter is 100 meter. If you write everything in terms of V, which is the pipe with the velocity with respect to the pipe. So, since the diameter is 100 mm and the nozzle is 50 mm. So, you can see that diameter is half of the pipe diameter, the nozzle diameter. So, you can see that we put in terms of velocity, it will be same with respect to, if you use the continuity equation A1 V1 is equal to A2 V2. So, from that we can write this VR square by 2G can be written as 16 V square by 2G. So, VR is in terms of with respect to the exit point. So, we are writing with respect to the velocity of the pipe. So, that is by 16 V square by 2G, since the pipe diameter is 2 times the nozzle diameter 50 mm. So, 16 V square by 2G, and then Z is 2 meter, and then say here also at the exit we assume the pressure as atmospheric pressure. So, P2 by gamma is 0, and then 0.5 V square by 2G, and then F is given as 0.02. So, FL V square by 2G, D is 0.1, the pipe diameter is 0.1 plus this K V square by 2G, K is given as 10. So, K V square by 2G plus 0.1, again this is given as the nozzle loss is 0.1 V square by 2G. So, now here with respect to nozzle diameter it is 16 V square by 2G. So, 0.1 into 16 V square by 2G. So, by solving this equation, by with respect to the Bernoulli's equation which you applied between the exit point and the reservoir. So, we get 25 is equal to 40.1 V square by 2G. So, we get V square by 2G is equal to 0.623. So, from this we get V square by 2G is equal to 0.623. Now, we can apply the energy equation from reservoir to the point L. So, here this L is just entrance point here at this location. So, we will apply with respect to the reservoir and the entrance location L here. So, if you apply the Bernoulli's equation, from reservoir to L. So, very similar way as we discussed in the previous case. So, the total head at the reservoir is 27 and then the atmosphere pressure. So, here it is 0, P1 by gamma is 0 and here it is the velocity head is say 0 the reservoir, and then at the location L is concerned there will be the velocity head will be V square by 2G and then P2 by gamma is the pressure head and then Z is the datum head, and then we have this 0.5 V square by 2G as the entry loss. So, the equation is 27 plus 0 is equal to V square by 2G plus P2 by gamma plus Z plus 0.5 V square by 2G. So, now from this we can get the HGL at L, that means hydraulic gradient line at L will be, we can take this P2 by gamma plus Z can be written as 27 minus, so this 1.5 V square by 2G, that is equal to 26.06 meter. So, thus we got the hydraulic gradient line at L, HGL at L is equal to 26.06 meter. So, now we can get the EGL, elevation of the EGL energy gradient line. So, that will be V square by 2G plus P2 by gamma plus Z. So, with respect to this, now we can, with respect to the HGL high elevation, we can add the V square by 2G. So, which is 6.623 as we calculated. So, 26.06 plus 0.623, that is equal to 26.683 meter. So, now the third point is we will be calculating elevation of HGL and EGL with respect to this location M. So, we will now use the Bernoulli's equation with respect to point M. So, that is 27 plus, which is the reservoir height head is 27 plus 0 is equal to V square by 2G plus P by gamma, P2 by gamma plus Z plus 0.5 V square by 2G, which is the entry loss, plus this we are considering the pipe length here. So, FL V square by 2GD. So, here this M is at 22 meter from here. So, we can write 0.020 22 V square by 0.1 2G as shown here. So, this is before the valve. So, from this we will get a P2 by gamma plus Z, which is the HGL elevation as 27 minus 5.9 V square by 2G, that is equal to 23.32 meter. And similarly, energy gradient line, if you add 0.623 as V square by 2G, we will get 23.943 meter. And then across the valve HGL drops by K V square by 2G. So, that is K is given as 10. So, we can see that it will be 6.23 meter. So, at end the hydraulic gradient line will be 23.32 minus 6.23, which is 17.09, and then EGL elevation will be 23.943 minus 6.23, that is equal to 17.713 meter. And then the last point at P, this is P here. So, at P we can see that again we apply the Bernoulli's equation. So, at the reservoir 27 plus 0 is equal to V square by 2G plus P by gamma plus Z plus 10.5 V square by 2G, including the entry loss and then this valve loss, plus 0.020, this 50 is the total length V square by 0.1 2G. So, now very similar way we can solve and get the elevation of HGL as P2 by gamma plus Z as 27 minus 21.5 V square by 2G is equal to 13.6 meter. And similarly, EGL and energy gradient line, we can add the velocity head 13.6 obtained from here plus 0.623, that will be 14.223 meter. And at R, that means the exit HGL is at 2 meter, which is only Z, and then EGL is Z plus VR square by 2G. So, VR square by 2G is 16 V square by 2G plus 2. So, that will be 11.97 meter. So, this we can plot like this. So, here this red line shows the HGL and this blue line shows the EGL with respect to this problem. So, like this we can solve various problems for the given given parameters. We can apply the Bernoulli's equation, and then various other losses are also considered here, and we can solve the problem. So, in the next lecture we will be discussing further about the pipe flow systems like pipe in series, pipe in parallel, we will be discussing.